I'm going to tell you about a scheme that does not actually have any heat network unit support. This one is entirely funded privately. It happens to be the largest system, or two systems as it is, in the UK. The title of my talk is based loosely on a miner's song, which goes from Biker Hill to Walker Shore, we're collier lads forevermore. I'm sure Dave will recognize that title. It's a song that these Geordie miners here would have known well. The colliers and the collieries may be gone, but not the workings. And it's these flooded workings which form the main reservoir for low-grade geothermal heat under Newcastle Gateshead. These miners' safety lamps are particularly relevant to our story, but we'll touch on them towards the end of my presentation. So here we are, Newcastle on Tyne, Gateshead, and the location of our sites is at Felling, just to the south of the River Tyne. Two warehouses, total area of 10,000 square meters, and these are used for storage of wines. Lanchester Wines is the developer of this project, or two projects. So this is an aerial view of the Abbotsford Road site, the first site. And those are the heat pumps in the plant room at Abbotsford Road. Installed capacity of 2.6 megawatts, but not developing the intended capacity. We'll look at that in some detail. This is the Nest Road site, another warehouse in which wines are stored. And this is the heat pump that's associated with that particular warehouse. It's half the capacity. This heat pump is working well. We've got significant comparisons to be made between the two sites. So what happens with the heat that's produced from the heat pumps? Basically, it is stored in a buffer tank, which we have here, and it's distributed through the warehouse using emitters on a flow and return pipework system, something like 60 emitters on this scheme. You can see the wines which are being kept at a very good temperature, and the output temperature from the heat pump is, yes, about 50 degrees when the systems are working properly. Just a bit of background in terms of the geology, coal measures, and heavily fractured. Now, normally the source for the heat that's being harvested by the heat pumps would be groundwater for a water source heat pump. But for a large industrial scheme, we need a lot of water, and the coal measures are not naturally highly permeable, and so we need something a bit more. Now we can see that we've got a built-up area, and if we move to the next slide, you will see the location of one of the mine workings that's under the site. So we've got those two sites there. So we've got Nest Road and we've got Abbotsford Road. And this, I'm showing you this information really with the intention of indicating the complexity of, or potential complexity of the situation under the ground. And it's particularly complex when you actually look into detail. And this was what was not done when the scheme was originally designed. It was originally designed with the intention of taking groundwater and putting it through the heat pump system and then discharging to the mine workings. This model of the Absard Road site shows abstraction boreholes over here and injection boreholes here. And unfortunately, the original drilling, which was planned by others, only tapped a very shallow aquifer, sandstone aquifer. The water, having gone through the heat pump system in the plant room here, was then discharged down to workings, which had been correctly identified, but the flow rate from the abstraction boreholes was inadequate to operate the heat pump system effectively. And this is the, this slide shows the output of the two heat pumps. We're only getting something like 30% of the installed capacity at Abbotsford Road, and this comes down to the wrong choice in terms of the target for extracting the water. There's 3 abstraction boreholes, 3 injection boreholes at Abbotsford Road, but not all are working. Only 1 abstraction borehole is working. So this is some work that's in progress, more of which later. Right, some key components and lessons identified. When GGS started working at Nest Road in 2018, the first thing we had to do was establish what we had in terms of boreholes, because there were existing boreholes on site, and we had to find out which ones could be developed successfully to complete the heat pump system. We needed to see cores of the strata, and we particularly required an experienced drilling contractor who understood how to penetrate multiple workings. So the coring works were carried out, these were successful, and we identified open workings at a depth of about 280 meters. And this seemed to be promising from the point of view of the injection capacity that we required in order to complete the system. We used the services of an experienced and local mining geologist consultancy to, first of all, help us with the mine records, which we obtained from the Coal Authority, and then to identify the different seams, the coal seams that were present. And this all helped with understanding what became apparent as an increasingly complex situation below ground. One of the fundamental requirements was to be able to complete the injection borehole to accept the amount of water that was required on this site. This was the Nest Road site. So we needed to be able to dispose of something like 60 litres a second. We needed to ream out the cored hole. Using a competent drilling contractor, we were able to do so, but that contractor used reverse circulation to advance through open workings. And it helps when they had the capability not only for carrying out closed circuit TV assessments of the state of the existing boreholes, but also to be able to measure verticality. And Dave has touched on the matter of deviation of boreholes. And when you're aiming for a target at some significant depth using conventional drilling systems without deflection, you really need to be able to keep the hole fairly straight, so drill collars and steady progress, and reverse circulation will help. Once the boreholes have been improved to a suitable standard, then pumping tests needed to be carried out. So that meant extracting water and from re-injecting in effect through a abstraction injection doublet. So there's no view of the water being discharged. It's all kept in the pipework. Fortunately, on this site, all the pipework had already been put in the ground. It was already assumed that things were going to work, but of course they weren't. But by adapting the existing system, we managed to achieve the goal. We're going to have a quick look at the actual mine water circuit. So this is the plumbing involved. So first of all, we have the abstraction borehole, which feeds into pipework, which comes into the plant room, and then it goes through a dirt trap, and then through electromagnetic meter and the essential interface between the heat pump and the mine water circuit, which is the plate heat exchanger, and then water is discharged back to ground through the injection borehole. Just some peripheral equipment. We've got the rather important piece of kit here, the building management system, with all the electronics in here to store the data from the various sensors and to control the peripheral equipment. And then we've got the borehole inverter and sine wave filter here. Monitoring and maintenance is key to understanding and maintaining the effectiveness of this heat pump system, and it requires a good team, really well experienced, although it has to be said there are not many people who have this experience at the moment. We find that we can get some very useful information from the BMS displays in terms of the discharge rate, ambient temperatures, borehole injection water levels and abstraction water levels. And then we have a nice visual display there showing what's going on with the boreholes. Here we have an independent engineer carrying out his inspection and assessment for the purposes of obtaining off-gem RHI support. And here's the heat meter that's been installed and upon which the RHI payments are measured. Now, problems. Don't want to stress too much the problems, but we believe these can be overcome. But something like this, you can see the accumulation of ochre, ferric hydroxide, in the intake to submersible pump. This is on the Abbotsford Road site, and this is where the borehole, you recall, was not installed to the right depth, so we didn't have the right amount of water. It was the wrong construction that had been designed in the first place. This is something which still needs to be rectified. This is ongoing work. Here we have the means by which we removed some of the ochre which was accumulating in the plate heat exchanger. Vigorous means necessary in order to shift the ochre which has come out of solution from the mine water. Dave has obviously covered this area. He also mentioned the use of oxalic acid. This is a water treatment. This is a dedicated chemical treatment plant that we had built, especially for removing the ochre buildup, but where there's a reduced water flow. Another problem that we found, these two photographs were taken only 3 months apart. So this is a sensor, water level sensor, a stainless steel, and this is what happened. You see intense honeycombing and pitting, the effects of dissolved hydrogen sulfide in the water upon the steel. And this is what happened to the electronics. This is a major issue when it comes to being able to keep an eye on what's happening with the water levels. We've had to replace everything, all these sensors, with titanium loggers. Now, this is a big problem, and it does need to be resolved if we're going to make any progress with these industrial schemes. just far too much paperwork. There's got to be joined up thinking. There's too many regulators. Why not have an integrated team that could particularly help developers with these schemes? I can't stress how important this is for the future. Question arises, what about the methane that might be down there? Well, we're talking about flooded workings, but of course, these workings tend not to be gaseous now, but they were in the past, and brings me back to this these photographs here of a Davy and a Geordie lamp, and they are particularly relevant here because if we take ourselves back to the 18th century, yes, the felling colliery was opened. Beginning of the 19th century, this is what the situation was here with a number of mines. This one particular, the Brandling Main, which subsequently became the Felling Colliery. It's 80 fathoms deep there. And this is the position of the old Felling Colliery as it was in 1812. Now, unfortunately, on the 25th of May, 1812, there was a massive explosion, probably caused by ignition from candles or from smoking that was the norm for lighting and refreshment down below. And sadly, 92 men and boys were killed at this place. Now, this is the Venture Pit, and this was the John Pit, and the William Pit was down here. The youngest of these of the miners at the time was a mere 8 years old, and they're buried here at Heworth. 91 of them, 91 bodies were recovered. I think it's a fitting tribute to remember all those miners who worked in the most appalling conditions, risking their lives daily below the site to secure for us what is going to be the energy requirements of the future. But unknowingly, they succeeded in creating a reservoir for the geothermal heat that's going to help to meet our energy needs for our low carbon future. Now that's the end of my talk, so back to Gareth.